So let me join the other speakers, thanking the organizers for having me here. And risking a bit, I've decided to talk about, let's say, dreams that we have, and to use this new area of gravitational waves to prove, or at least try to see if we can learn something about what we call string cosmology. So I understand that there has not been any lectures on string theory, let alone string cosmology. So hopefully I'll just give you the ideas that we have on doing that. And so what I will be talking about, at least in this talk, will be based on different works that I've been doing in the last years in collaborations with various peoples here. So, okay, so definitely we are here because this first detection of gravitational waves definitely has opened up a new way for us to study and understand our universe. And definitely one very exciting possibility, although very challenging, which was there already before the discovery of gravitational waves from binaries, was the possibility to measure primordial gravitational waves produced in the very early universe, in particular during the cosmological evolution, cosmological inflation. And these primordial gravitational waves are actually a generic prediction of inflationary models, but their amplitude is typically very, very small. So most models will give you something small that is not really relevant for any experiments, current or future ones. However, as well was already observed before, but has been an active research, is to understand that there may be more, and we are trying to study those cosmological scenarios where this primordial spectrum may be enhanced at different scales, and then we may have a possibility to actually see those waves with future gravitational wave experiments at different frequencies. So, of course, as people working on trying to understand a bit beyond and understand the origin of all this in terms of a consistent theory of quantum gravity, our hopes are high, and we would like to understand if it is possible to use this new tool to understand something about quantum gravity, and in particular, perhaps models of cosmology and string theory. So what we would like to understand is at least try to know what are the properties of at least string-motivated cosmology models that can enhance these primordial spectra at different scales, so giving rise to gravitational waves at different frequencies, accessible to experiments, detecting different frequencies. So maybe we will be able to constrain models and parameters of our string theory constructions. So again, I know there are many students here, so I apologize because there will be no proper introduction to string cosmology, but I can, of course, I have to advertise our recent review on string cosmology, and where some of the things I'll say are there. And although we did not have much on gravitational waves, probably we'll have to do an update because many of us are now moving into more gravitational wave cosmology aspects of string theory constructions. Okay, so I'll try to cover two of these possibilities. One will be mostly based on supergravity, but the idea is that we can actually follow that through and embed it into a more string theory construction. And this will be in the context of multi-field axion monodromy inflation, and I will explain a bit more what is that. So I understand maybe inflation was discussed by Sriram Kumar, so hopefully it will not be so new material. And in the second part, again, something here has been mentioned is a possibility that non-standard cosmologies that may follow from some type of scalar tensor theories, which arise very naturally in string theory constructions, models of cosmology, may actually enhance the gravitational wave spectrum at different scales. Okay, so when we are constructing models, in particular models of cosmology from string theory, we have lots of things. We start with 10 or 11 dimensions, but at the end of the day, for cosmology, we want to focus on the scalar sector. And at the end of the day, so there are several other sectors we are going to ignore. For inflation, we are interested in the scalar sector. And in general, there will be several scalars. Most of what I'm going to say, all that I will say, is just focusing on two scalars because that's sufficiently simple that we can say things, and we already there can understand many of the features. So in general, we'll have to be working, and we'll see later, with in the context of n=1 supergravity. But at the end of the day, if we don't really care about where everything's coming from, we can boil down the action in the scalar sector to this form, where at least we have to identify two things, which is, so there's one or more scalars, well, more scalars in general. And in general, those scalars will describe some scalar manifold whose metric is given by this function of the scalars themselves. So in general, will be curved, non-flat. And and on the other hand, of course, there will be a potential which is usually constrained by precisely n=1 supergravity. So in general, the potential is not just any function that I like, but I have to compute all the action from my theory. So generally speaking, we will have both potential couplings between the scalars as well as kinetic energy couplings between the scalars coming from this function. Okay. So okay, so we want to do cosmology. So at the end of the day, we have the equations of motion. Okay, this is something you probably have seen. And for two scalars, well, we will have, in principle, two equations for two scalars. So, okay, that's fine. And here, this is the full kinetic energy of all the scalars. Okay, and so since we want to study slow roll cosmology, slow roll inflation, I want to review a little bit how slow roll inflation looks like in the case of multi-field, many more fields, because it's a little bit different, and this you may or may not have seen already. So in order to understand slow roll, the slow roll conditions, it's neater and for more transparent to decompose the equations in terms of the tangent and the normal projections of the inflationary trajectory. Okay, so I just project my equations along those directions. So Friedman equation remains the same, but now instead of these two separate equations for the scalars, I have these two equations. So this one looks very much like a single field kind of standard inflation, except that this derivative of the potential is just the one projected along the tangent direction. And then there is something that normal projection gives me this, this other equation, where this a turning rate appears, which is going to be a protagonist in what I'm going to say next. Okay. So we can go further. and write down the projections along these tangent and normal directions of the Hessian elements of the potential along these directions. And these are exact expressions. Exact expressions give me these relations between these projections and these parameters that I'm defining, that you immediately, if you have seen inflation, you will immediately identify, well, these are the slow roll, standard slow roll parameters. Epsilon telling me whether there is acceleration or not, and the eta also, which has to also be small. And also there's a third parameter appearing here. But what happens when there are more than one scalar is that a new parameter appears, which is this new parameter, which is nothing more than the changing rate of this dimensionless turning rate that I introduced before. So if anyone is familiar with dBi inflation, you may start to see similarities, because there also a new slow roll parameter appears associated to the speed of sound in that case. Okay, so if we look at what are the conditions for slow roll, meaning that along this inflationary trajectory, the potential has to be sufficiently flat, sufficiently long time. At the end of the day, this in this case can be translated to these conditions being very small, which gives the usual relation between the potential being dominated by, the h square being dominated by the potential energy standard. However, in this case, we also find that these conditions, this happens, so these relations hold. And moreover, importantly here is that a new slow roll parameter appears, which is precisely this changing rate of this new parameter. So again, if you are familiar with dBi inflation, there's the similarity with some parameter which is called S there. It's similar, very similar. Okay, so why do we need all this? Well, now we know what this means. And so now we stick to something, the simplest possibilities we can have, which is two fields, and we can even be even more concrete and write exactly the kinetic term in this fashion, which is equivalent to several other forms. And the equations of motion take this form, where here derivatives, are with respect to number of efforts, not time. And so in principle, you have these equations and you have to solve them. So there are several branches that you can have for these solutions, depending precisely on what kind of function you have and also what kind of initial conditions you have. But there are two cases which have been studied recently, which are the more relevant for what I'm going to say next. So one of them is called large, slowly varying turning rate, where this turning rate, dimensionless turning rate, happens to be large and smoothly increasing during the whole inflationary evolution, but the slow roll parameter associated to this new turning rate remains small. And one perhaps more interesting from the point of view of gravitational waves in particular, for which we are here, was precisely is that of having sharp turning rates. So in other words, cases where this turning rate suddenly is large for a short time, and this was indeed observed by Christoph, who is here, together with Sebastian and the Gonzalo Palma and collaborators. So this one seems like very interesting, and then it has been studied in, like, phenomenologically, what kind of spectra this can give, etc. And yeah, so at this point, of course, people like me will ask, well, okay, that's very good, but can we actually realize any of this, and in particular, this kind of scenarios in, let's say, supergravity or perhaps string theory models, and what will be the prospects? So we explore that in this work, and what we saw is that, well, kind of an easy way to get these transient large turns, things like this, can arise through transient violations of slow roll, and moreover, also taking inspiration from some other work I've been doing in the past. One can realize that actually a natural way to do this is to actually have inflation using an axion field, where you include also what is known as subleading correction. So in other words, because I did not write. So So you may be familiar with natural inflation, where theta here is an axion. And so what happens in the case of axion monodromy is, while in this case you have a discrete shift symmetry which is preserved, by having this, essentially what happens is that there is some contributions that break this shift symmetry, and you have now new terms that can come with, let's say, some constant, some powers of your field, plus, let's say, the cosine. But in general, if you are actually computing this in particular from axions that appear in your string theory, what happens is that you may have indeed further corrections which are subleading, coming from non-perturbative corrections that are subleading, but you can also have terms that come with powers different powers of the axion itself. But in particular, so this essentially you have, if you consider, for example, a square potential, that will be like just the potential. If you focus only on this, and this you assume these are very, very, very small, so they don't show up. But the moment these subleading corrections become relatively important, you start to see modulations in your potential. Now, this actually arise very neatly in the context of two-field axion monodromy inflation, and in particular in the case of supergravity. So what we did was to focus on supergravity and look at the supergravity construction. And I know there has been no supergravity here, so this is just in case you have seen supergravity. I give you what will be the so-called Keller potential, superpotential, out of which we construct the scalar potential. As you see, is a non-trivial function of these two functions here, one real function, one holomorphic function, where here these parameters are the important bits which will come from your theory, and those will be the parameters we ideally want to constrain, etc. So we don't really want to know much about the supergravity case, but at the end of the day, we can write down in terms of the real fields how the kinetic term looks like and how the potential looks like at the end. So what I want to stress here is that while if you are doing just a field theory phenomenological model, you may just choose any potential you like for the purposes that you like. Once you actually try to do something, in this case, in the supergravity context, you don't have that much freedom. And in particular, we see that if we want to include these modulations, they come with a price. The price to pay is that there's a non-trivial coupling between the two fields, which arises, so in particular in this case, with an exponential, so there is some kind of separation, but it also comes back here, this field. So message here is that, well, we have to deal with the coupling, which of course make things more complicated than you would like, right? Because if we could just get rid of this coupling, maybe we could get something like analytical or so. We could not. So, but what is nice is that this simple model gives us these very interesting kind of trajectories. So here we choose just very specific parameters, and we see what is the evolution of the inflationary trajectory. So here is just a zoom of the trajectory, part of the trajectory. So we see how indeed this modulated trajectory is happening. And in terms of what the slow roll parameters are doing, we see two important things. One, epsilon is always less than 1. What does that mean? It means that inflation never stops. Okay, so that's important because there are models where inflation actually stops, and that's, for example, double inflation. Okay, this is not. And on the other hand, is that there are slow roll violations where the second slow roll parameter is bigger than 1. So these are the transient slow roll violations I was talking about. And then we see that indeed this dimensionless turning rate indeed has all these nice sharp turns that were proposed as a possibility to enhance the power spectrum and give rise to primordial black holes, for example. So here I also plotted the masses of, or the eigenvalues of the masses of the scalar fields along the inflationary trajectory, because both of them happen to be larger than the Hubble scale, contrary to perhaps what is normally expected. Okay, so what are the results? Where indeed, so we choose some parameters such that, of course, we could get some enhancement of the power spectrum. And so these are the different choices that we took. And here this is P zeta or PR that we find. So this kind of profile is clearly very, very non-trivial. So with all these modulations. And in terms of PVHs, of course, it gives a non-trivial mass spectrum, which may lead to different types of abundances at different ranges, keeping the whole abundance small. But what I really wanted to mention about this model is the predictions for the result for the induced gravitational waves. So this has been discussed in all the previous lectures. So here is just the result of what we get for this kind of power spectrum. So we see a very broad and large. Of course, we are choosing, remember, we are choosing our parameters such that we see something with a very characteristic modulated shape. And well, of course, that will be our dream, that this can indeed be proved in the future experiments. So is this the end, or is it that's it? Okay, so first of all, yes, it's very interesting that actions always are very interesting, and if you actually take into account also subleading corrections that usually are there, even more interesting phenomenology can arise. And however, there are challenges. So in terms of this particular model, the CMB constraints are not quite right. So we need to do some modifications to that. And also at this point, we were mostly focused on trying to, I mean, from the pure supergravity point of view, you don't really need, you can do much more than if you try to embed this in a full string theory construction. So ideally, what we would like to is to have a full embedding in a string theory model, inflationary model, to instead have the range of values that we can have in such a model and see what they give for the different spectra. So that's something that we are working also now. But at least it does offer a concrete model where these modulations appear, non-trivial profiles, etc. Okay, so So I have some time for the second part. So in this second part, okay, I want to focus on the post-inflationary evolution and just to discuss what kind of cosmologies that we are going to call non-standard cosmologies can happen motivated by some specific type of non-scalar tensor theories. Okay, so this has been mentioned before, but here the idea is to consider the fact that, well, we have our cosmological, standard cosmological model where we assume there was inflation happening early on, and then in principle reheating happened, and then radiation started to dominate. Eventually BBN happened, matter domination, and eventually we arrive here. Now, one of the important things, and in fact, is something that many people are exploiting, because now with the access to, the tool of gravitational waves, we can actually access all this period, which is otherwise highly unconstrained. So all this epoch is kind of a free epoch where we can explore many things that may can happen. And in fact, the typical possibility is that there may have been a non-standard kind of cosmology happening due to different types of, for example, new degrees of freedom, etc. So I think it has been mentioned, maybe kination domination, early matter domination, and some other types of non-standard cosmologies. All can happen here, so long as by the time of BBN, you are back to standard cosmology. So this really offers a window where indeed many people are exploring different types of gravitational wave signals to access this epoch. And the kind of case I want to consider here is scalar tensor theories, which are precisely motivated from kind of stringy cosmological models. Okay, so let me first very briefly introduce this kind of scalar tensor theories. So in general, in scalar tensor theories, what you have is, of course, gravity and a scalar. And what was observed by Bekenstein in 1992 was that besides the usual conformal relation that you can have between two metrics given by some function c of the scalar, the most general kind of relation you can have is actually includes also the kinetic energy of the scalar. And in particular, these functions, actually C and D, can also depend on the kinetic energy. So in this case, I'm just leaving that out. So besides this conformal type of relation, which preserves angles, you can also have what Bekenstein called a type of disformal relation between the metrics, which is associated to these kinetic terms, and which distort angles. Now, if you are just, proposing some functions C and D, you just need to check that they satisfy what is called a causality constraint. So, okay, so this is very general. But what happens is that, well, in string theory, scalar tensor theories arise naturally. We have several scalars, we have gravity. And those that are very interesting for what I'm going to say is those that arise in deep brain models of cosmology and particle physics. Now, what happens in this case is that there is an extended objects, which is called deep brain, some extended object. And if you look at the induced metric on that brain, the induced metric takes exactly this form. So it precisely matches what the form that Bekenstein was proposing with C and D just functions of phi itself. Now, in the context of a deep brain, an actual deep brain construction, the what happens is that the longitudinal fluctuations of such an object correspond to matter, you can associate it to matter, while the transverse fluctuations correspond to a scalar, and these two, through the brain, both of them are coming from the brain, and they couple each other precisely through this relation. So this is what we call as, so they couple this formally through the action that describes the brain. So I'm sorry, I'm not giving any like details, but hopefully the idea will be more or less there. And anyways, yeah, I'll be here also next week, so we can discuss, feel free to ask. So the cartoon is that we have string inflation, of course, where reheating happens, radiation follows, and we have possibly a stack of the brains where matter and radiation and everything is living, and this type of matter is coupled to a scalar associated to these transverse fluctuations through precisely this type of conformal and disformal functions or way through the induced metric on that brain. So that's the cartoon, of course, even a more cartoon here. And but in what follows, I'm just going to completely describe a field theory picture of this. And what we'll see is that if we consider, just focus on this formal kind of coupling, in particular just being a constant, what happens is that this already modifies in an interesting way the gravitational wave spectrum, which can enhance it at different scales. Okay, so again, just we write our action, and what's key here is, well, two things. So we are now including matter. Now we are post-inflation. So important to observe here is the kinetic term for the scalar. So surely you haven't seen, this is not the common one. It's indeed coming from the d-brain action, dBi kind of action. So it's a non-standard, what we call non-standard kinetic term. And this is what basically is causing the enhancement. And then matter living, again, is living on, we assume is all in this 4D brain. But a key thing here is that the matter here is coupling to this twiddle metric, which for what follows, I'll consider this G being just, the C, the conformal coupling, just being a constant, just one, while the disformal coupling being just a constant, like so. Now, if we were to think about an actual d-brain construction, this M will be some scale associated to all the parameters in the theory, the brain tension, string coupling, warping, wrapping, etc. We are not going to do that for now, so we just consider this. So again, we have to look at our equations of motion. Here things become more complex. Now we have radiation, matter, and the scalar. So just to, what we have to look up here is, now this W is not the dimensional starting rate. This is the equation of state, which includes any changes from 1/3 due to species becoming non-relativistic. And what is key here is this gamma. So this gamma is coming precisely from this square root. So it's what we call the Lorentz factor. And this is encoding the kinetic energy of the scalar. And that's what exactly is causing the deviation from the standard expansion. So on the other hand, lambda here encodes basically the potential energy of the scalar. Okay, so the modified, so we are looking, what are we looking for? We are looking for how the expansion rate gets modified due to the presence of this non-trivially coupled scalar to matter. So the modified expansion rate is given by this formal Hubble parameter h twiddle, and we can measure how much it deviates from the standard evolution via this parameter that we define here, xi, which can be neatly written in terms of these parameters. So at the end of the day, what's important is this gamma. So gamma encodes the kinetic energy, and lambda again is the potential energy, which in the early evolution will be irrelevant. It's a potential, it's not important then. And so one of the important constraints here that arises is that since we need to make sure that the standard evolution is recovered by the onset of BBN, we need to make sure that whatever evolution happens, whatever change is happening, it should be over by the time of BBN, where this psi should be 1. Okay, so that's actually a strong constraint. And so we put it to the test. And what we do is, well, again, so during the very early evolution, the potential is irrelevant. So this lambda is essentially 0. And the enhancement of the expansion rate is due, as we saw in the xi term, precisely by this kinetic energy. So we can understanding as a kind of dBi kination domination epoch, which enhances the Hubble parameter and gives rise to this. So this here is the modified expansion rate, the red, and the blue is the standard. It goes back to 1, so everything is normal by BBN and nobody knows anything. So one interesting thing here is that we can choose in principle M as we please until we actually make contact with the string theory, say. But the one observation is that the smallest value that we can choose for M such that we recover BBN is associated to around the QCD scale. So that's an interesting observation. On the other hand, because we have this non-trivial modification of the expansion rate, this is going to, and this enters into the gravitational wave evolution, this enhancement is going to lead to a primordial gravitational wave enhancement. And at the end of the day, we can write precisely omega GW in this way, and we see again here our kinetic, this gamma factor, which precisely is telling us about this kinetic, dBi kinetic domination. And PT is just the primordial tensor spectrum. So of course we want to write this in terms of frequency because we want to associate to different experiments. And but what's interesting for this type of models is that depending on the initial conditions, this enhancement in the Hubble parameter and then in the PBA, in the primordial gravitational wave spectrum, can happen at different frequencies which are relevant for different experiments. Now you may say, well, but then you can have anywhere, but on the other hand, if we happen to have the rise at the right scale, we may be testing this type of theories. Now what's interesting as well is that the enhancement due to this type of this formal coupling has a very, very, very distinct profile. So here you can ignore these two, sorry about that, and just focus on the solid line. That will be the one that I have described up to now. And so again, the important thing is that by choosing different values of this formal scale M and the initial conditions, also for the initial temperature, etc., we can move around this peak, but the peak, the profile is always, has always the same kind of behavior. Now, one interesting, since I have little time, one interesting possibility that we exploit with this was to have the rise precisely at the NANO-Grav scales. And this happens precisely for this type of masses where the M, the scale M is precisely around the QCD scale. And again, The interesting thing is the profile, which has very specific types of slopes. And yeah, so that was an interesting, let's say, playground that we play just to explore further this type of scenarios. So, okay, I can finish here. I just wanted to say that after this evolution, eventually the potential will be relevant, and you can play around with this, and we play around with the possibility that your potential can have contributions that can give you a period of early dark energy as well as late dark energy. But okay, this is a bit of just playing around. So maybe I just finish by saying that definitely gravitational wave cosmology is offering us an excellent opportunity to test models of cosmology which are derived from consistent theories of quantum gravity, and definitely we think we should take the opportunity, even though there are, of course, several challenges, but hopefully we'll learn something. So I finish here.
So questions?
I'm wondering about the scale M. So when you introduced it from this D-brane picture, does it correspond to some aspect of the geometry of the D-brane?
No, it will mostly be related to, it depends which kind of brain you took, but it will mostly come with the brain tension. So indeed, these very low values will be too low. Unless maybe if you have some higher dimensional brain and then you wrap it, you do, but you will do to some gymnastics. But indeed, that QCD scale low value is a little low. It usually will be higher. Yeah. Mm-hmm.
So I have a question regarding that multi-field inflationary models and axion monodromy inflation. So, so in single field models, after the inflation, field rolls down and just oscillate, and then leakage happens and reheating happens. So in multi-field models, how these things happens, because there are lots of couplings involved between those scalars. So how the field oscillates and how reheating happens.
So the fields will oscillate as well around the minimum, and it could be, it depends. So it will depend. You may have one which is heavier than the other one. That you will have to look. So probably, yes, you have to look a bit model by model, but there is a minimum for the fields. Couplings will be more complex because you will have to worry about couplings of the two fields to anyone, and then see whether there's a hierarchy, who's decaying what, who is decaying into what. But the minimum is there, and the fields oscillate around the minimum, both of them.
Okay,
yeah.
So you were expecting similar reheating phase for this inflator?
Yes,
two field models?
Yes, but more you complicate your life more. But yes, I mean both of them oscillate,
okay.
so I'll expect similar.
Yeah. Okay, thanks. Mm-hmm.
Yeah, so I was just wondering if VNN plays any role in this case, and if not, what's the reason behind that?
VNN?
VNN?
No, so that's actually a very good question, good observation. Why is VNN not there? So that one you cannot write, that's a bit more model dependent, and you cannot write in a neat way. It's kind of the other component. If you write this as a matrix, yeah, that component, yeah, it's not, you cannot write in such a neat way. It depends a bit on your model, what you have. Then you can say something, but otherwise, no. It's not very good.
Hello. Yeah. Ma'am, can you go to this probably 19 number slides where actually we plot the
19?
19 GW spectrum. Yeah, this is this
Oh,
previous one.
sure.
Yeah,
Oh, no.
no, this one. So probably here you can see that when we change the value of lambda by m, the strength gradually increasing, and after certain time the strength again come down. Is there is any physical reason or
Yeah,
just
with observation, yeah, we observed, but we could not see very well a pattern, why it's going down again. Yeah, that's true. Mm.
So any questions, comments?
So just as a crosstalk between different talks, my entire presentation was about how VNN looks like and what are the consequences.
Ah, perfect. I was not in your talk. Yeah, so yeah, you can go back to his talk to this to see a VNN. Mm. Yep.
So any other questions, comments? So if not, let's thank Professor Zavala once again. So we'll be back after lunch.